If we had n different, not identical particles that were approximately not interacting, at least in some region of space and time, for example, before or after some scattering, then we could construct the state for those n different particles by simply multiplying together the single particle states or modes as follows. So particle 1 in state A, particle 2 in state B, particle 3 in state C, and so on. And the numbers here refer to the particles, and the capital letter N refers to the particles, and the small letters refer to the single particle state the individual particles are in. So we're going to continue to use this notation as we go forward here.
Now suppose the particles are identical. Even with many particles, it should still be true that swapping any two identical particles should make no difference to any observable. We can follow through the argument as before and find that swapping the same particles a second time should get us back to where we started. And again, we would therefore find that swapping any two particles once again multiplies by +1 for bosons or -1 for fermions. Suppose we have more than two bosons. If all the particles are identical bosons, and we are interested in the state of the set of bosons, where one particle is in mode A, and another is in mode B, and another is in mode C, and so on, then we can construct a state, what we can call the general symmetric state, that consists of a sum of all the conceivable permutations of the particles among the states.
So, for more than two bosons, we can write that state in the following form. This is a sum over permutations, and this entity here with a hat over it, the p hat, is one of what we'll call the permutation operators. And a permutation operator, of course, it's an operator, so it changes one function in Hilbert space into another, but in this case it does it by permuting the particles among the modes. The meaning of this sum here is that it is taken over all of those possible distinct permutation operators. So it's a strange notation, but it's a convenient one. So what do we mean by this? Well, obviously one term in this sum is for the identity operator, being the permutation operator. It doesn't do anything at all. So that term in the sum would just be particle 1 in state A, particle 2 in state B, and so on. Another term in this sum would be one where the particles have been permuted. That would be particle 2 in state A and particle 1 in state B, and so on. And another term in the sum would be where particle 3 is in state A and particle 1 is in state C. Or we could have another term in the sum where particle 3 is in state A, particle 5 is in state B, particle 6 is in state C, and so on, for some permutation of the particles among the states. So the idea of this notation is saying that we're going to add up all of the different possible permutations of particles among states. And we'll formally do that by using this notation of a permutation operator. So we can think of the permutation operator as being something that takes this state and turns it into another state in which it's different numbers possibly that are in here, and we still use all of the numbers from 1 up to capital N. So it's a slightly strange notation, but the meaning is that this summation is over this kind of state, but with all possible permutations of the particles among the states. Now, this notation here then is just a mathematical way of saying that we're summing over all the permutations of the n particles among the chosen sets of modes. And for this boson case, it's quite allowable for two or more of the modes actually to be the same mode. That is, it's quite allowable for B to be the same state as A in this list. So we could have a list that is 1A, 2A, 3C, and so on. That's an allowable list for bosons, and then we'd be considering all of the possible permutations of that. When we do this, incidentally, we get a relatively complicated formula for what should be the prefactor out in front of this sum. So for the moment, we're not stating that prefactor explicitly. We will eventually get back to understanding how to write that. But For the moment, we just put in a proportionality sign because of the complicated nature of the formula for that particular prefactor. And this ability that we can have multiple different particles in the same mode, of course, is an important and very general property of bosons. Note that for any given set of modes, A, B, C, and so on, with given numbers of these bosons in each mode, there is only one possible such boson state of identical particles. This state here that we've written out satisfies the symmetry requirement that swapping any two particles does not change the sign or amplitude of the state. That's because swapping particles in these permutations here merely corresponds to changing the order of the terms in this summation here. So if we write down this boson state here and then say, oh, let's swap particles 1 and 2 here, well, all that means is that we have exactly the same terms in the sum, but just in a different order, because there will be a permutation operator that corresponds to swapping them back in this list. For more than 2 fermions, we can write the state there in a similar notation. In this case, we put a plus or minus in front of the permutation operator, and we have to clarify what we mean by that. So by this notation, we mean that we use the plus sign where the permutation operator we're talking about corresponds to an even number of pairwise swaps of the individual particles. That is, if we had a permutation such that we had swapped 1 and 2 and also 3 and 4, that would be 2 pairwise swaps, and we'd have a plus sign in here. And the minus sign then, by contrast, is when the permutation corresponds to an odd number of pairwise swaps of the individual particles. So if we had only swapped 1 and 2 with a particular permutation operator, we would have a minus sign in here. Or if we'd done 3 pairwise swaps in a particular permutation, swapping 1 with 2, swapping 3 with 7, swapping 9 with 53, then that would be a minus sign that we would put in front of that particular term in this overall sum. Here, incidentally, with fermions, it's much easier to count the number of possible terms in the sum. It comes to n factorial, so this factor out the front for normalization just becomes 1 over the square root of n factorial, and it's easy to write it explicitly. Note that for this fermion state we've written here, for identical fermions, if 2 of the single particle states are identical, for example, if B and A are actually the same state, then this sum adds up to exactly 0. Because for each permutation, there is then an identical one with the opposite sign that exactly cancels it. So if A and B are the same state, we have one term in the sum that is plus all of this we see here, with A and B being the same. And then we could swap 1 and 2 between those two states. That would be a single pairwise swap, and that would give us a minus sign for that term in the sum, and so the sum would cancel out. This, therefore, is the extension of the Pauli exclusion principle to n particles. Now, there's a particularly convenient way to write the n-particle fermion state, and that's called the Slater determinant. So this is the notation for the Slater determinant. This expression here with these vertical bars, of course, is just expressing the determinant of all of these elements here, as if they were elements in a matrix, for example. But we're just using this as a mathematical notation here. And it turns out that the general formula for a determinant is exactly this expression that we just wrote down here. So everything between these lines, which is the determinant, is exactly the same thing as this summation here. And in fact, this notation is sometimes used as a formula to write down a determinant.
Remember from the theory of determinants that, first, the determinant is 0 if 2 of the rows are identical, which here corresponds to the Pauli exclusion principle, and second, the determinant changes sign if two of the columns are interchanged, which here corresponds to exchanging two particles.